Am I audible? Hello?
Yes. Yes.
Okay, thank you. Is my screen visible?
Yes.
Okay, thank you. So good evening everyone, welcome to this NPTEL live session for the NPTEL course Introduction to Machine Learning. So this is the second live session, and in this live session we will discuss some practice problems for the week 2 topics. In week 2, linear regression and feature selection, these methods have been taught. So we will discuss some practice problems on those topics. And if you have any questions or doubts, you can ask me in this session. I will also try to answer your questions and queries. So we can start the problem solving part of this session. After that, if you have any questions or queries regarding the week 2 contents, you can ask me. So this is the first question. Given a training dataset of 10,000 instances with each input instance having 17 dimensions and each output instance having 2 dimensions, the dimensions of the design matrix used in applying linear regression to this data is, so there are 4 options: 10,000 into 17, 10,002 into 17, 10,000 into 18 and 10,000 into 19. So what will be the dimensions of the design matrix that will be used in linear regression on this training data set, which has 10,000 instances and 11 dimensions in each input instance and 2 dimensions in each output instance? So you can write your answers in the chat. So most of you have answered C, which is 10,000 into 18. Okay. Does anyone think any other option other than C would be correct? Does anyone think that any other option would be correct? So I got one answer, D by Vidyasaran. D is 10,000 into 19. Okay. All other answers are C. So the correct answer here is actually C. So most of you have answered it right. So the design matrix basically means the X matrix that you will see in case of linear regression. So in linear regression we try to model X as model Y as Y equals X into beta. So this is what we try to model Y as. So here X will contain the whole training data set. So there are 10,000 instances in the training data and there are 17 dimensions in the input, but you also have to include the intercept dimension also. So the intercept is not included in this 17 dimensions, so you have to include it to the training data set. So a total 18 dimensions you would have in the design matrix in that case. So it would the X would look like this. So there will be 10,000 instances, and there will be, so 10,000 rows, and total 18 columns would be there in X, the design matrix. 17 input dimensions and 1 intercept, which is not included in the input instances. So this is how you will get the answer. So C is the correct option, 10,000 into 18. So it doesn't matter how many output dimensions you have, because design matrix is just X, which is the training data. So which is basically the input data, and output dimensions do not matter in that case. So it would be 10,000 into 18.
Can you kindly repeat why it's 18 in place of 17?
So 17 dimensions are there in each input instance. So basically 17 input features are there, and you have to include the intercept, which is not generally included in the training data. So are you able to understand what I'm trying to say, the intercept?
Yes, thank you.
Yeah. So the intercept is the extra dimension which you will have to include in the design matrix. So that's why it would become 18 columns. So this is the second question. This is on PCA, or principal component analysis. So which of the following is false about PCA? PCA is a supervised learning method. It identifies directions that data have the largest variance. Maximum number of principal components is less than equals to number of features, and all principal components are orthogonal to each other. Which of these following is false about principal component analysis? These are the 4 options. So you can write your answers in the chat. So many of you are writing option A here, which is PCA is a supervised method. Okay, so any other answers in the chat? So I got one answer is B. Ankit Kumar Dwivedi has written B, which is it identifies the direction that data have the largest variance. Okay. All other answers are C here. Sorry, A here. Indumati Nagaraj is saying B. Ali Aman is saying B. Okay, some of you are saying B, but most of you are saying A. So the correct answer here is A, because you have to find out the option which is false about PCA. So PCA is an unsupervised learning algorithm. If you have gone through the lectures, PCA is principal component analysis. So if you have gone through the video lectures, you will understand that PCA is an unsupervised learning algorithm. So it doesn't use the output or target variable or the Y as we use in machine learning. It doesn't use the target variable or the output variable. It is solely based on the input features or the X in case of machine learning. So as it does not use the output variable or the target variable, it is an unsupervised learning algorithm. So it uses only the input features to reduce the number of features in the data. So option A is the correct answer. It is actually a non-supervised learning algorithm, but the option says it's supervised, so option A is the correct answer. Option B, many of you were saying option B, but this is uh, this is actually true, so that's why it will not be the right answer. It actually so it identifies the direction that the data have highest variance. This is the actual objective in PCA, that it tries to find out the components in the data or the directions in the data that the data have the highest variance. So this is actually true, so that would not be the correct answer here regarding PCA. Aravind J has asked this question accurate. It's in week 2 assignment. So the following is in limitation.
Sorry, it looks like except one, all others are already limitation of subset. So that's why just wanted to check if this question itself is accurate or not. It is asking, the question is to find the limitation
Yes.
of subset.
Yes, these questions have not been said by us, so we will not be able to answer this. This has been these assignments have been set by the instructor and the regular TAs for the course. So if the question
How to validate with them, because we don't know how to check with them whether this question itself
no,
is
if the
wrong.
question is wrong, in that case they would remove the marks for this question, so the question would be would not carry any marks in that case. But week 2 deadline is not over, so in that case I will not be able to
Yeah,
answer.
that's fine. That's totally
Yeah.
understandable. That's okay. But just wanted to check whether this question is wrong or not, because there are multiple limitations.
Yeah, so the regular TAs and the instructor creates this assignment and the test question paper. So if there is something wrong in these questions, then they would obviously remove this question, and the question would not carry in marks if this is not correct in that case. So you have to wait for the evaluation of week 2 after the deadline is over.
But do you agree that this question has issues?
Of selection and population, they tend to produce biased estimates of values, and they cannot handle dataset from missing values. They are computationally expensive for large datasets. They assume a linear relationship between independent. Yes, they are not suitable for datasets with categorical predictors. No, the question, in my opinion, the question is correct, and
So you mean that there is only one limitation, and all others?
is this question single correct answer or multiple correct answer? If it is a
Actually, single correct answer.
no, I mean, so I think the question is not wrong, but you have to wait for the correct answer. When the evaluation is done, they will be able to.
Okay, sure, no problem. Thanks.
So now we move on to question 3. So this question is on KNN regression or K nearest neighbor regression. So your the given below is your dataset x1, x2 and y. So x1, x2 are the two features in the data, and y is the output variable or the target variable that you have to predict. And you will use KNN regression or K nearest neighbor regression with k equals 3. So what is the prediction for a new input 3, 2? So 3, 2 is a new input that will be given to you, and you have to predict the output for this point 3, 2 using this KNN regression where k is equal to 3. And you have to use Euclidean distance measures to find out the distances between points. You can write your answers in the chat. So in k-n regression, you try to find out the k nearest neighbors of the point given to you, and you take the average of y values of all the k nearest neighbors. So this is what you do in k-n regression. So here k is 3, so basically you have to find out the 3 nearest neighbors of the point given to you. 3 comma 2 is the new input given to you. You have to find out the 3 nearest neighbors of this point 3 comma 2, and you take the average of the y values of those 3 nearest neighbors. That would be the output value for the new input 3 comma 2. So I have already got one answer in the chat. Ritika Gupta saying 2.5, which is option D. Okay. Hetal is saying D. Okay, so I got 2 answers in the chat. Both of the answers are option D. Ankit Kumar Devidi is also saying D. So in k-n regression, we try to find out the k nearest neighbors of the point given to us. So the new point given to us is this 3 by 2, this point 3 comma 2. This is the new point, and we will try to find out the k nearest neighbors of this point 3 comma 2. Okay, here k is 3, so 3 nearest neighbors you have to find out from the dataset. This is the whole dataset, and you have to take the average of the y values of those 3 points, and that would be the y value for the new input point 3 comma 2. So the correct answer here is option D. So it would be easier if you plot the points or plot all the points on a 2D plane. So it would become much easier to find out which are the closest points. So there are 1, 2, 3, 4, 5, 6 training points are given. So you have to plot those 6 training points. 1, 2, 3, 4, 5, 6 points are plotted, and then this red point, this point is the new input for which you have to find out the prediction. So you can find out the coordinates of each point using this x1 and x2. These are the 2 coordinates, x1 and x2. So from this graph we can find out that this and this, these are the 3 closest points to this red new input point. So we will the closest points are these are the closest points 2, 2, 3, 3 and 4, 1. These are the 3 closest points, and you will have to just find the average of the y values of these 3 points. So y values of these 3 points are already given here. So in this y column it is given. So the y value of 2, 2 is 2, y value of 3, 3 is 3, and the y value of 4, 1 is 2.5. So you have to take the average of all these 3 points, and it will be 2.5. So that's why option D, 2.5, is the correct answer.
Sir, but in question it says use the Euclidean distance, right? So if you try to go by that route, how do you
so I mean, yeah, Euclidean distance is just the distance between this and this you have to find out. So Euclidean distance is simply x1 minus x2 whole square plus y1 minus y, I mean in this case y, not y exactly, but y, here y is the x2 point. So this is how you find out the Euclidean distance. So if you find out Euclidean distance, you will find out that these are the three closest points, isn't it? If you just plot those points on a 2D plane, and you can simply see which are the closest points. Those are the points with the least Euclidean distance values from the test point. So you can also do the same thing using the Euclidean distance measure. So x1 and x2, these are the two dimensions you have to use for finding out the Euclidean distance, not the y is the output value. So you have to use the dimensions x1 and x2 to compute the Euclidean distances, and the same result you will get as you are getting from this graph. So both the methods are correct, so there is no problem. You just have to find out the three closest points. So is there any other doubt in this question? Okay, so we can move on to question 4 now. So consider the following statements. Assertion and reason. Two statements are given. So assertion says that orthogonalization is applied to the dimensions in linear regression, and the reason for that is orthogonalization makes univariate regression possible in each orthogonal dimension separately to produce the coefficients. So the assertion A and reason R are given, two statements are given, and the options are which whether A and R, whether both of these two are true, or R is the correct explanation of A or not. So these are the 5 options. Both A and R are true and R is correct explanation of A. Both A and R are true but R is not the correct explanation of A. A is true but R is false. A is false but R is true, and option E is both A and R are false. So these are the 5 options regarding these two statements. So you have to find out which of these options is correct. Arvind J is saying A, which is both A and R are true and R is correct explanation of A. Okay. Anyone else? Sayandeep says B. So B is A and R are true but R is not the correct explanation of A. Yes. So the two statements are given, the assertion and reason. Two statements are given. So assertion says orthogonalization is applied to the dimensions in linear regression, and the reason statement R says that the orthogonalization makes univariate regression possible in each orthogonal dimension separately to produce the coefficients. So you have to find out whether both the A and R are true, or R is the correct explanation of A or not. So these are the 5 options given. So you have to find out whether both the assertion and reasons are true or not. So I got many other answers in the chat. Most of the answers are B, and some of you have also said D. One C option is also there in the chat. So most of you are saying option B. So the correct answer is A here. So we have to apply orthogonalization in case of linear regression. If we don't apply orthogonalization, in that case, if the different dimensions or different features in the data are correlated to each other, in that case the coefficient values would be wrong. So we will not be able to find out the actual relation between the output variable and the input features. So orthogonalization is applied. Assertion is certainly correct, And reason is also correct that orthogonalization makes univariate regression possible in each orthogonal directions separately to produce coefficients. And the R is the correct explanation of A, that R says why we need orthogonalization. So orthogonalization makes the univariate regression possible in case of linear regression, otherwise we will not be able to apply univariate regression on each of the features or dimensions in the data. So by using orthogonalization we are able to apply univariate regressions of after finding out coefficient for one variable, we orthogonalize the other features and then find out the coefficient for the next variable. In this way we apply univariate regression multiple times to find out the coefficients for each of the dimensions. So the statement R is the correct explanation of A. So option A is the correct answer here. So most of you have written B, but the correct answer here is A. This is question 5. So suppose we want to add a regularizer to the linear regression loss function to control the magnitudes of the weights beta. So beta is the weights of the linear regression, which we multiply with the data matrix X. So we have a choice between these two regularizers, so sigma 1 beta and sigma 2 beta. So these are the two regularizers we have. In the first regularizer we are just taking the modulus of the weight matrix and sum it up for I equals 1 to p for p features. And in case of the second regularizer, we are taking this is basically L2 norm of the weights, and we are summing it up for I equals 1 to p. So which one is more likely to result in sparse weights? So this is the actual objective of using regularizers, that we want to reduce the number of features, so we want sparse weights. So which of these regularizers will produce sparse weights? There are four options. Option A says the first one, option B says the second regularizer, option C says both the regularizers will result in sparse weights, and option D says neither of these will produce sparse weights. So I have already got many answers in the set. So all of you are saying option A. So one student is asking what is meant by sparse weight. So sparse weight means many of the weight values would become 0. So if there are p number of features, we get p plus 1 number of weights. So in case of sparse weights, most of those beta values or the weights should be 0. So that way we can reduce the number of features. So the weight for a feature becomes 0, that means that feature is no longer being used in the regular linear regression. So that is what I mean by sparse weight. So most of the answers are option A, and one student is saying option C. C is both sigma 1 and sigma 2 will result in sparse weights. Okay. So here the correct answer is option A. Option A is the correct answer. Sigma 1, which is the lasso regression or lasso regularization. If you have gone through the video lectures, you'll be able to understand. So in case of this first regularizer, we are using L1 norm of the weights. So by using L1 norm of the weights, and in the second regularizer it uses the L2 norm, that's why beta square is there. This is called ridge regression. The second regularizer is called ridge regularizer or ridge regression. So and it is well known that the lasso regularizer or the L1 norm is able to produce sparse weights, and so the correct answer is option A. So this is because of the shape of the regularizing constant that we get from the lasso constants of L1 norm. So that's why because of that shape of the constant, where the shape of the lasso regularizer is actually like this, lasso constant, and in case of ridge the regularizer looks like this, because this beta square, so this would, the constant should look like a circle, and as this is using the L1 norm, beta modulus of beta, so in case of lasso or L1 norm, the constant should look like this square. So this is why option A is the correct answer. So the explanation of this is already given in the video lectures. You'll be able to find out from there also. So now moving on to question 6. The model obtained by applying linear regression on the identified subset of features may differ from the model obtained at the end of the process of identifying the subset. During 4 options are given. So in forward stepwise selection, backward stepwise selection, forward stage wise selection, and D is all of the above. So question is, the model obtained by applying linear regression on the identified set of subset of features may differ from the model obtained at the end of the process of someone started presenting, I think Devi Govindan, can you please stop your presentation? So I hope my screen is visible again.
Yes.
Okay. So so the question is, the model obtained by applying linear regression on the identified. So after identifying the subset using a certain feature selection method, now we are applying the linear regression, and this is the first model, and the second model is model obtained at the end of the process of identifying subset. So while finding out the subset, we are also creating the model. So these are the 2 models, and in which case of in which subset selection method these 2 models would be different. So some of you are saying C, some of you are saying D. One correct answer is A here given. Okay, so any other answers in the chat? Rohit is saying C, Indumati Nagaraj is saying C. Okay, so most of you are saying C, some of you are also saying D, and one student is saying A. Okay, so the correct answer here is C, which is forward stage wise selection. So in case of forward stage wise selection, while creating the subset of features, we create one model, because in forward stage wise selection, and every stage what we do, at every stage we try to find out the feature which has the highest correlation with the residual at that point. So basically we are applying univariate regression at every stage to find out the next feature that we will include in the subset. So we are applying univariate regression at every stage, so that way we are already creating a model while finding out the subset. And after finding, if we after identifying the subset, if we apply linear regression and find out the model, those two models might be different because the coefficients would be different, because the model that we created while identifying the subset, the coefficients would be different because we are not using the features that have already been added to the subset. But in case of the first model, where we are using the identified subset of features and applying linear regression, in that case we are using all the features at the same time, so the coefficients would be different, so the result would also be different. The two models would be completely different. But in case of forward stepwise and backward stepwise selection, we are not creating the model while identifying the subsets. We are greedily trying to add one. In case of forward stepwise selection, we are greedily trying to add one feature from the set of all features into a subset, if it improves the performance of the or accuracy of the model. And in case of backward stepwise selection, we remove one feature at a time, unless until the error or the accuracy reaches some cutoff value. So in that case, we are not creating models while identifying the subsets. In case of the forward stepwise selection and backward stepwise selection, but in case of forward stage-wise selection, while trying to identifying subset, we are creating a model, and after identifying the subset, we can train another model. Those two models might be different. So that's why option C is the correct answer. So many of you have said option C. Some of you have also said option D. So option D is not correct, because in forward stepwise and backward stepwise selection, we are not creating any model while identifying the subset. This is question 7. So in question 7, consider forward selection, backward selection and best subselection with respect to the same data set. So which of the following is true regarding these three subset selection methods? Forward selection, backward selection and best subset selection. So option A says best subset selection can be computationally more expensive than forward selection. Option B says forward selection and backward selection always lead to the same result. Option C says best subset selection can be computationally less expensive than backward selection. And option D says best subset selection and forward subset selection are computationally equally expensive. And option E says both B and D. So basically you have to find out which of these are more computationally more expensive than the others. So this is what you have to find out in this question. Three subset selection methods are mentioned here: forward, backward and best subset selection. So which of these three are actually more computationally expensive than the others? So Nayana is saying option A in the chat. Okay. Anyone else? Shayandeep is saying A, Vidyadharan is saying A. Nishti Pandey is saying A. So Indumati is saying D. So I got one answer D and all the other answers are A. Hital is saying option A. Kiran is saying A. So most of you are saying option A, and the correct answer is option A. So three subset selection methods are mentioned here: forward subset selection, backward subset selection, and best subset selection. So the first two methods, forward and backward selection, both the methods are greedy methods or greedy algorithms, where in case of forward selection we try to add one feature greedily from the set of all features to our subset, and in case of backward selection we try to greedily remove one feature from the subset that improves the performance of the model. And in case of best subset selection, we are trying to find out the optimal subset of features. So best subset selection is actually much more computationally expensive. You have to go through all possible subset of features that you can create from the set of features. So this is not a greedy algorithm, so this is computationally much more expensive. So that's why this option A is correct, that best subset selection can be computationally more expensive than forward selection. And forward selection is very linear in nature, and at every iteration you try to add one feature from all the set of all the features that improves the performance of the model. But in case of best subset selection, you try to find out the optimal subset of features. So you have to go through all possible subsets that you can form out of the set of features. So that's why option A is correct answer. Now moving on to question 8. Principal component regression, or PCR, is an approach to find an orthogonal set of basis vectors which can be used to reduce the dimension of the input. Which of the following matrices contain the principal component directions as its columns? So you have to follow the notations that are given in the video lectures. So based on the notations, matrix notations used in the video lectures, you have to find out which matrix contains the principal component directions as its columns. So I have got 2-3 answers in the chat. All of the answers are option D, which is V. Is there any other answers? 3-4 answers are already given. All of the answers are option D here. Indumati is saying option D. Okay, so all the answers are option D so far. So the correct answer is option D, which is the matrix V. So as it is already shown in the video lecture, that in principal component analysis or principal component regression, we try to decompose decompose X as U D V transpose. This is the singular value decomposition of X. And this V is the matrix which will contain the principal component directions as its columns. So option D, V is the correct answer. So all of you have said the correct answer in the chat. This is question 9. Let A, which is an M cross N matrix, be a matrix of real numbers. The matrix A transpose has an eigenvector X with eigenvalue B. Then the eigenvector Y of A transpose A, which has eigenvalue B, is equal to 4 options are given. So X is an eigenvector of the matrix A transpose with eigenvalue B. Then you have to find out the eigenvalue B of A transpose A, which has the eigenvector Y. You have to find out the eigenvector Y of A transpose A, which has the same eigenvalue B. Four options are given: X transpose A transpose X, and last option is cannot be described in terms of X. So to find out this eigenvector Y of A transpose A, so eigenvector of A transpose is given, and the eigenvalue is also given, which is B. So we have to find out the eigenvector Y of A transpose A. So Indumati is saying option B, Srinivasa is saying option B. Okay, any other answers in the chat? Nana is also saying option B. So I have received 4 answers in the chat. All of the answers are option B. So has anyone else computed this? So here eigenvector and eigenvalue for this matrix A transpose is given. So we can write it as A transpose X equals B into X. So this X and B, the eigenvector and eigenvalue for this matrix A transpose is given. So we can write it write this equation. And now if we multiply A transpose to both the sides, we multiply A transpose to both the sides. Now we take this A with this A transpose, so this will become this A transpose A transpose X equals B A transpose X. So you can see that this is the matrix for which we are trying to find out the eigenvector A transpose A. This is the matrix, and we have created this matrix in this equation. So this is the vector. So the vector is appearing on both the sides, left hand side and right hand side. A transpose X. So this is the eigenvector of this matrix A transpose A, and the eigenvalue, corresponding eigenvalue is B. So that means this has to be the eigenvector with the eigenvalue B for the matrix A transpose A. So A transpose A is the correct answer. This. So this is how you have to compute the eigenvector for the matrix A transpose A. So eigenvalue and eigenvector for the matrix A transpose is given. You have to find out the eigenvector of A transpose A having the same eigenvalue. So this is, you just have to multiply this A transpose to both the sides of this equation, and then you have to separate out this A from here, and you form this matrix A transpose A. So that way you are getting this vector A transpose X. So option B is the correct answer. So is there any questions or doubts in this question? Okay, in that case we can move on to question 10. So in question 10, this is again our matrix. Let U be a n cross 1 vector such that U transpose U equals 1, and let I be the n cross n identity matrix. The n cross n matrix A is given by I minus k U transpose. So this is given that A is I minus k U transpose. K is a real constant. U itself is an eigenvector of A. A is this, and U is an eigenvector of this matrix A with an eigenvalue minus 1. So what is the value of K? So you have to find out the value of K from here. So it is given that U is an eigenvector of A with eigenvalue minus 1, and U transpose U equals 1. So this is also given. So you have to compute the value of K. Dhruvesh is saying option C. C is 2. Okay. Indumati is also saying option C. Any other answers in the chat? Srinivasa is saying option C. So all of you are saying option C. Satyam Gupta is saying option B, -1. Okay. Satyakant is saying option C. So here the information that are given here is that u is an eigenvector of A with eigenvalue -1. So from this you can write AU equals -u. So this is what we can get from this question. So A is given, A is I minus KU U transpose, this one. So I minus KU U transpose into U equals -u. So if I simplify this, it would come as U minus K U U transpose U equals -u. So U transpose U is 1, this is given here. So from this we can write U minus K U equals -u. So that means 2u equals ku, 2 minus k into u equals 0. So that means u is not 0 certainly. So 2 minus k is 0. So 2 minus k is 0. So k equals 2. So this is how you have to compute this. So the eigenvector and eigenvalue for A are given. So from that information you can compute everything. So k is 2, which is option C. So many of you have written option C in the chat, so this is correct. Is there any questions or doubts on this question? So we can move on to question 11. So bias and variance can be visualized using a classic example of a dart game. So these dart boards are 4 dart boards are given for 4 different players on the right hand side of this slide. We can think of the true value of the parameter as the bullseye on a target, and the arrow's value as the estimated value from each sample. Consider the following situations and select the correct options. So basically you have to find out which player has higher variance than the others, which player has higher bias than the others, from the 4 boards that you can see for 4 different players. So option A says player 1 has low variance compared to player 4, player 1 has higher variance compared to player 4, and option C says bias exhibited by player 2 is more than that done by player 3. So this is player 1, this is for player 2, this is player 3, this is for player 4. So these blue dots in each of these boards are showing the predictions. Basically in case of machine learning terms, they are the predictions, and the red circle is the actual target value. So from these 4 dart boards you have to find out which player has higher variance and which player has lower variance. So 3 options are given here. Indumati saying option A, Hetal is saying option B, Srinivasa is saying option B. Okay. Shayandeep is saying option B and C. Vidyadharan is saying option B, Nana is saying B and C. Anyone else? So the correct answer here is option B only, not B and C. Some of you have said B and C, but the correct answer is only option B. So for player 1, we can see the bias basically means the error in prediction, how much the predicted values are from the actual target value. So for player 1, these are the predicted values, and this is the this is the actual target value. So the bias is high for this, because none of these blue dots are anywhere close to this bullseye. So for player 1, bias is high and variance is also high, because the predicted values are quite spread out, so the variance is also high. Now in case of player 2, the bias is low because the points are very much closer to the bullseye. So bias is low. Bias is the difference between the actual value and the predicted values, expected value of that. So the bias is low here. The predicted values are very much close to the actual values, but the points are very much spread out again, so variance is also high. In case of player 3, the predicted points are close to the bullseye, and the variance is also low. Most of the points are concentrated into a very small region, so both bias and variance values for this player 3 are low.
Can you kindly tell for player 1, how did you guess the bias and variance differently? Like what?
So bias is the difference. The bias is basically the error you are getting, which is the difference between the target value and your predicted value. So your predicted values are here, all the predicted values are here, and the actual target value is this red bullseye. So all the points are very much off the actual target value. So bias is high. Bias means basically the expected error of your predictions. And variance is high because the points are very spread out. The points are not concentrated into a small region. The points are very much spread out. The variance is high. So that's why bias and variance, both the values are high for player 1. And in case of player 4, the variance is low because the points are concentrated into a very small region, so variance is low, as we can see. But the bias is high. Bias because the points are not anywhere close to the actual target value, so the error is there. The error is quite high, so that's why bias is high for this player 4. So based on this analysis, option B is correct, because player 1 has higher variance compared to player 4. Player 1 is certainly high variance, and this is low variance. Obviously this is concentrated within a very small region, but in case of player 1, this is completely spread out. So player 1 has higher variance. Other options are not true, because option A says player 1 has low variance compared to player 4, which is certainly not right. Player 1 has high variance. And option C says bias exhibited by player 2 is more than done by player 3. The bias of player 2 and player 3 are very much similar. In both the cases, in case of player 3, all the predictions are within this bullseye region, so bias variance both are low. And in case of player 2, though the variance is high, the points are very much close to the actual target value, so the bias would be low. because bias takes the expectation of the difference between the actual value and predicted value. If you take expectation, then in that case, even though the values are very much spread out, in case of player 2, the bias would come low. So that's why option B is the correct answer. So now we move on to question 12. This is the last question, I think, of this session. Which of the following are true for any m cross n matrix A of real numbers? So 4 options are given for any m cross n matrix A of real numbers. First option says row space of A is same as the column space of A transpose. Option B says row space of A is same as row space of A transpose. Option C says eigenvectors of A transpose are same as eigenvectors of A transpose A. And option D says eigenvalues of A transpose are same as eigenvalues of A transpose A. So which of these 4 options is correct? So many of you are saying option A and D. And Satyakant is saying only D. Okay. Indumati is saying only A. So some of you are saying both A and D, and some of you are saying only A and only D. Any other answers? So the correct answers are A and D. So most of you have answered it right in the chat. So A is very obvious because when we take the transpose of a matrix, columns become rows and rows become column. So row space of A is same as column space of A transpose. So this is obviously correct. Option D is eigenvalues of A transpose are the same as eigenvalues of A transpose A. So you can easily find it out. So so the calculation is already given here. So for A transpose, if X is the eigenvector and lambda is the eigenvalue, so we can write this equation A transpose X equals lambda X. Now if we multiply A transpose to both the sides and we take out this A, so it becomes A transpose A into A transpose X equals lambda into A transpose X. So that means this becomes the A transpose X becomes the eigenvalue, this becomes the eigenvector, and lambda is the eigenvalue. So that means lambda is also the eigenvalue of A transpose A. Lambda was taken as the eigenvalue for A transpose, and we can also show that lambda is the eigenvalue for A transpose A with the eigenvector A transpose X. So that means option D is also correct. And the other options B and C are not correct, you can see, because row space of A might not be the row space of A transpose, and eigenvectors of A transpose, eigenvectors of A transpose and A transpose A are not same, but the eigenvalues would be same. This lambda is the eigenvalue, but the eigenvector was X in case of A transpose, but in case of A transpose A, eigenvector is A transpose A. So that's why option C is not correct. Eigenvectors might not be same, but the eigenvalues would be same for A transpose and A transpose A. So these are the 2 correct answers here. So these were the practice problems that I wanted to discuss in this live session. So if you have any questions or doubts regarding any of the problems that I have discussed today, you can ask me now.
Sir, on the second question, forwards stepwise selection, backwards stepwise selection, different from the stage wise. So if I understand correctly, we eagerly
In which
sorry
question?
question sorry
Let me see which one. In
yeah,
this question?
sorry, yeah,
Yes.
sixth one. So here, forward stepwise selection and backward stepwise selection, we take features in greedy method, right?
Yes.
So here you mentioned that in each step we don't create model. So, but in stage wise, forward stage wise, we build model every time.
Yes.
So that's why you mentioned that the models are mixed. So can you explain that one more
So
time?
in case of so the other two methods, forward stepwise and backward stepwise, these two methods are greedy methods. So in every iteration, either we are adding a new feature greedily or removing a new feature greedily, but we are not creating a model in that process of identifying the subset of features. So this you can observe from the two algorithms, forward stepwise and backward stepwise. But in case of forward stage-wise selection, so if you say the algorithm for this, so in every iteration we try to find out the feature that has the highest correlation with the residual at that point. So this is given in the video lecture as well. So we
So
try.
it's forward stepwise also we do the same, right? Because we pick in the forward stepwise take a some small subset of the features. We find the highest correlation.
Yeah, and in case of forward stepwise, we don't find out the highest correlation. I mean, in case of forward stepwise, we take a new feature which is not already present in our subset, and we add it to a subset, and we create a model, and we're trying to find out whether the accuracy has improved or whether it has declined. So based on that, we will either add it or we will not add it. So in that case, the and finally the model that we get. We are not creating a model in the process while identifying the subset. We are just training the model to see whether to add that feature or not. So the model that we will get is the final model after identifying the subset of features, and then we train the linear regression and get the coefficient values. But in case of stage wise, at every iteration we run an univariate regression to find out the feature with the highest correlation with the residual. And so as we are running the univariate regression in every iteration, we get the coefficient for that feature. So based on that we get one model while creating the subset, and after getting the subset we can run linear regression again on the subset that we have received from the stage wise selection, and those two models might be different.
Okay, okay, okay. Thank you.
Is there any other questions or doubts? Question 1. So in question 1, 10,000 instances are there in the training data. Each instance has 17 input features or input dimensions, and you have to find out the dimensions for the design matrix. Design matrix is nothing but X, and in X is like this. So each row is an instance, training instance, and each column is an input feature. So 70 input features are already there in the input data, and we will have to add one intercept feature as extra. So intercept is not included in the training data, so you have to add that to our design matrix. So that's why 17 plus 1, 18 would be the number of columns in the design matrix. That's how we get 10,000 in cross 18 as the dimensions for the design matrix. Kanishka is saying which book I should study if I've studied only basic concepts. So you can ask this question in the discussion forum of this course. The course instructor and the regular TAs would be able to answer which books you should follow for that. So you should ask that question in the discussion forum. So if there are no other questions or queries or doubts, then we can end this session here. Thank you everyone for joining. We will again thank you everyone. So we will again have another session next week on next Tuesday.